Day to everybody. So let's continue with our lecture. In our last lecture, we have discussed the topic on open propositions, and we have mentioned in that discussion that an open proposition is actually a declarative statement, and this declarative statement will now involve variable or variables, but this declarative statement or this open proposition has no truth value yet. So that's the main difference between the open proposition and the previous discussion on propositions, the truth value. And this open proposition can now be converted into a proposition that is if when the variable or variables do get their respective value. And there are two ways of doing that. One is by assigning a specific value for our variable, or we can use quantification. We have given some examples on assigning a specific value. Of course, that is very simple. You just assign a specific value for the variable involved. On the other hand, we can also use quantification. Then under quantification, we have two types of quantification. We have the universal quantification and the existential quantification. For the universal quantification, we use this symbol, the inverted letter A. So this is now read as for all x in our uh, proposition Px, or we can now have this as the functional notation of our function. So we use a capital letter and the variable involved. There are more variables involved, then we just add the variables after the first variable separated by commas. And we have the second type of quantification, which is the existential quantification. And for the existential quantification, we use the inverted letter E, followed by our variable, and then followed by our functional notation. And this is now read as there exists an x, there exists a value for that variable x such that it will now satisfy the open proposition. And what's the main difference of these two? Of course, the main difference of these two will now be on how we will be considering the truth value of the proposition. So for the universal quantification, for all, so this means that for all the values of x, and where do we get the values of x? We now need what we call our uh, universal set. And in this case, our universal set or our universe of discourse, every element in that universe of discourse must satisfy the condition given to make our open proposition to be true. So that should also mean that if there is one value in the universe of discourse that will not satisfy the condition given, then the proposition will now get a truth value of false. On the other hand, for the existential quantification, we just need one value. We just need one value from our universe of discourse to satisfy the given condition. One value is enough to say that the proposition will now be. For today, let's discuss the examples given in your notes. Actually, the examples that we will discuss are the problems stated there as homework. And we have two parts. Letter A, determine the truth values of the following. And for the following open propositions, we are now considering the universe of discourse as the set of positive integers. We have the set of positive integers. We have 1, 2, 3, and so on. So we have infinitely many elements in this set. So we have the set of all positive integers. And for the first one, if we will now determine the truth value of this, we have the universal quantifier for all. So for all x, the proposition given is if x is a prime number, then x is odd. If x is a prime number, then x is odd. So remember, this is our open proposition. And our universe of discourse is the set of positive integers. So if we now consider all the possible values of x, for this open proposition to be true, then all the possible values of x must satisfy our condition. And when we choose an x from the set of positive integers, the first part is x must be prime. And what is again a prime number? A prime number is a number whose factors would be 1 and itself. 1 and itself. So if we will try to list down some possible elements here, what are our prime numbers? We have 1, we have 2, 3 is a prime number, 4 is not a prime number, 5 is a prime number, 7 is a prime number, 8 is not a prime number, 9 is not a prime number because it's divisible by 3, 10 is not a prime number, it's divisible by 5, 11, and so on. So we still have other uh, prime numbers. We have infinitely many prime numbers. So looking at our sequence again, we want to show or we want to determine the truth value of this open proposition. Provided that we are now considering all positive integers that will now fall under this condition. X is prime and at the same time x is odd. So if we will look at this one, is there an element we can find that will violate the proposition? So if you will look at our initial list, you will find here that 2 is a prime number, but it is not odd. It is an even integer. Since 2 is since 2 is not an odd integer or is not an odd prime number, therefore that now becomes our counterexample. Therefore, this proposition will be having a truth value false because of element 2. 2 is prime, but 2 is not odd. The condition that we want to satisfy there is if x is prime, then x is odd. 2 is prime, but 2 is not odd, which makes now our proposition to be false. Next example, we have two quantifiers here. And in our discussion last meeting, we have said that if we want to determine the truth value of our proposition involving two quantifiers, we always work from left to right. We have for all x, for all y, and we now have our open proposition, x is odd and y is odd, okay? But this is an if-then statement. So if you would like to modify this uh, proposition, we can maybe add a sign of grouping there. So we have if x is odd and y is odd, then x times y is also odd. Okay, so did you get that? So what we are saying here is we are now looking at the universe of this course as the set of all positive integers. So when you get a value of x, it must be an integer, and at the same time, it must be odd. When you get a value of y, it must be an integer, positive integer, and it must also be odd. So if you get x is odd and y is odd, then x times y is also odd. So what are we having here? Get a positive odd integer, multiply it by another positive odd integer. The result must be an odd integer. So if you will try to figure this out, if you want now to determine the truth value of our proposition, so maybe we can look at some examples, but of course, when we are proving, uh, we must generalize our proof. So in this case, if you get, just to illustrate, so let's say your x is positive 3, your y is, let's say, positive 5. So let's just take an example. We will now say x is 3 and y is 5. We get x times y is equal to 3 times 5, which is equal to. So this example tells us that uh, 3 is odd, 5 is odd. When we multiply them together, the resulting is odd. But remember, we want to generalize this. So if we want now to explain this, this is the more appropriate way of showing this. Uh, when we want to represent x to be an odd number, we can let x, let's say, be equal to 2 times n, where n is an integer, and then we add 1. Okay, where n is an integer. So in this case, n is a positive integer. Why positive integer? Because x is positive odd integer. So remember from algebra, when you multiply any integer by 2, that will be even. And if you add 1 to that even value, it will now become an odd integer. So that is now the representation of x. Now let's have also y. So let y be equal to, this time, 2m. M is again another integer, then plus 1, where m is a positive integer as well. So we now have made a general representation of x and y. X and y are odd integers. So if we want now to consider x multiplied by y, then x multiplied by y will be equal to 2n plus 1 multiplied by 2m plus 1, because because x is represented by 2n plus 1 and y is represented by 2m plus 1. And if you will now expand this, we now get 4nm plus, so we're just expanding this, plus 2n plus 2m plus 1. And looking at this closely, we now get, what do we get? What do we get here? We now get, uh, looking at the first three, looking at the first three expressions here, we can factor out 2. So that should now give us 2 multiplied by 2 and m plus n plus m, and then everything we now have plus 1. Okay, so what happens here? Remember that n and m are positive integers. And if you get an integer multiplied by an integer, by closure property, this would still be an integer. And again, by closure property, you take an integer plus an integer plus an integer, the result will still be an integer. And then, since this is a positive integer because n and m are positive integers, then this entire thing is a positive integer. You multiply it by 2, then this entire expression here will now be an even integer because it's multiplied by 2. And you add 1, therefore an even integer plus 1 will make it as an odd integer. Therefore, that now shows us that if x is odd and y is odd, then x times y is also odd. Therefore, if we will now answer this, therefore, our proposition will now get the truth value true. Okay? So for all x, for all y, if x is odd and y is odd, then x times y is odd. Next example, we have there exists a w such that 2w plus 1 is equal to 5. What does that mean? Since we are now using the existential quantifier, it only tells us that we just need one value of w that will satisfy this equation. So how do we do that? How do we find a possible value for w? Using our algebra, we have 2w plus 1 is equal to 5. So using our algebra, this will now become 2w equals 5 minus 1 is 4. And if we now divide both sides by 2, we get w is equal to 2. So what does this mean? If w is equal to 2, this value of w will now satisfy the equation. And since our quantifier is there exists, it will only mean that we just need one possible value of w that will satisfy this statement. Since we have found a possible value of w which satisfies our universe of discourse that it is a positive integer, then this proposition will have a truth value of true also. Okay, next example. Next example is there exists an x such that 2x plus 1 is equal to 5, and this should be x squared. X squared is equal to 9. So what is this all about? We are now looking at the existential quantifier. There exists. So we just need one value of x that will satisfy this statement that 2x plus 1 is equal to 5 and x squared is equal to 9. And how do we do this? So let's look at the first part of the proposition first, which is the section having the value 2x 2x plus 1 is equal to 5. Let's look at this first. And 2x plus 1 is equal to 5. This gives us 2x is equal to 4. Therefore, x is equal to 2. On the other hand, for x squared, equals 9. For x squared equals 9, using now our algebra, of course, if we extract the square root of both sides of the equation, we get x is equal to 3. But we know that from algebra, when we extract the square root, we get two possible values, plus and minus. But we don't use now the negative value. Why? Remember that whenever we get a value of the variable, it must come from the universe of this course, which is the set of positive integers. And if you consider minus 3 here, it will not belong to the universe of this course because minus 3 is not a positive integer. So if you will look at this, uh, in the first part of the proposition, a possible value of x that will satisfy this proposition is 2. While on the second part of the proposition, a value of x that will satisfy this proposition is x is equal to 3. And our connective here is and. So that should mean now that for these two propositions to be satisfied, the first proposition, x is 2, x is 3. Therefore, that clearly tells us that there is no value of x that will satisfy both propositions at the same time. And since this is a connective and this is a conjunction and both propositions must be true so that the entire proposition will be true. Therefore, since we cannot find a value of x that will make each proposition here to be true, then this entire proposition must now have a value, truth value of false. Okay. We now go to the second part of the homework. Still, determine the truth value of the following sentences where the universe of this course is the set of integers. So in the earlier example, we have just considered the set of positive integers. This time, we are considering the set of integers. Okay. So for number 1, for all x, we want to satisfy x squared minus 2 is greater or equal to 0. For all x squared minus 2 must be greater or equal to 0. Okay, so if you will now analyze this part carefully, our universe of this course is the set of integers. So this is for all integers must satisfy this condition. But if you will look at this part here, we have mentioned that if we want to show that the proposition is false and if the quantifier is the universal quantifier, we just need one value that will violate the statement given. So if you will look at this one, if if x, let's say, is equal to 0, isn't it that 0 is an integer? If x is 0, what do we get? We have 0 squared minus 2 is minus 2, right? Substitute it here. You have 0 squared is 0, minus 2 is minus 2. Question, is -2 greater or equal to 0? Okay, -2 is not greater or equal to 0. Let's copy that and let me substitute here the value 0. We have zeros. If x is 0, 0 squared minus 2, is it greater or equal to 0? Isn't it that -2 is not greater or equal to 0? Since -2 is not greater or equal to 0, then this means now that our proposition will be false. Why false? Because not all elements in the universe of this course will satisfy this condition. We found here one value that does not satisfy this condition, making now our statement false because we have the universal quantifier for all. How about the next example? For all x, again, for all integers. For all integers, this set of integers must satisfy x squared minus 10x plus 21 is equal to 0. Okay, so from algebra, given now our quadratic equation, x squared minus 10x plus 21 is equal to 0. So if we will solve this, recalling our algebra, what's the easiest way to solve this? We can solve this by factoring. Factors of x squared, of course, we have x and x. Factors of 21, we have 7 and 3 to give us 21. And since we need a minus 10 there, we can have this as minus x minus 7 and then x minus 3. So if you will double check, you have x times x is x squared, minus 7 times minus 3 is positive 21, minus 7x minus 3x is minus 10x. And then from there, this now gives us x equals 7 and x equals 3. So what does this mean? This line tells us that only x equals 7 and x equals 3 will satisfy this quadratic equation, x squared minus 10x plus 21. But the universal quantifier here is for all. For all. So anong sinasabi niyo dyan? Dapat lahat ng integers satisfy niya tong equation na to. But from this solution, we have seen that there are only two possible values of x that will satisfy this. Since not all integers will satisfy this quadratic equation, therefore, the truth value of our proposition will be false. Again, why false? Because only x equals 7 and x equals 3 will satisfy this equation. How about number 3? So to make this true, we can change the quantifier. There exists there exists an integer such that an integer will satisfy this. We have seen here that there are two integers that will satisfy. Remember, when we use there exists, we just need one. One value of x, one value of an integer that will satisfy this. Since we have found two possible values from the previous problem, therefore, the truth value of this will be true. Okay? So we're using the same proposition, we're using the same universe of this course, but we're just changing the quantifier from a universal quantifier to an existential quantifier. For a universal quantifier, all the elements in the universe of this course must satisfy the condition to make the proposition true. For the existential quantifier, we just need one value of the variable to satisfy the given condition to make the proposition true. Okay? How about the second example, the fourth example? So for the fourth example, if you will consider this, okay? So if you will consider the next example, we have for all x, for all integers, our integers must satisfy the condition that x squared minus x minus 1 is equal to 0. For all integers, x squared uh, x squared minus x minus 1 is equal to 0. So if we will now look at this quadratic equation, let me use first our quadratic equation, changing this to equal first. Let me just change that to equal so that we can solve this. By using, we cannot factor this because you can try factoring. You will not be able to factor this because this is uh, if you will try to factor, what are the factors of x squared, x and x? What are the factors of minus 1? Minus 1 and positive 1. So if you will try to use those factors, you will not get the middle term. Therefore, if we will now solve this, we can use what we call the quadratic formula. And the quadratic formula states that x is equal to minus b, where b here is minus 1, okay, plus or minus, plus or minus, plus or minus, okay. Anyway, just rewrite this properly. Minus 1 or minus b plus or minus uh, the square root, of b squared. So the square root of b squared, b squared minus 4 times a times c. Do you still remember this? This is what we call the quadratic formula. Then everything divided by, again, the quadratic formula is minus b plus or minus the square root of b squared minus 4ac all over 2a, where 2a is 2 times minus 1. So, simplifying this, we now get x equals, that will be positive 1 plus or minus, that's plus or minus the square root of minus 1 squared is 1. We have minus 4 times minus 1 times positive 1 is positive 4. Then everything divided by negative 2. So before we proceed with this one, if you will look at our resulting value for x, let's just compute this. We have here square root of 5. And we have here 1 plus or minus the square root of 5 all over minus 2. So it means now that the resulting roots here wouldn't be uh, real numbers but not integers. Not integers. Resulting values are not integers. Okay, so let's now analyze. Let's go back to this one. So just if you want to continue with the roots of x, just solve for the roots of x. You will get 1 plus or minus the square root of 5 all over minus 2, which means that since square root of 5 will not give us an integer, then the possible roots will not be integers. So, what do we have here? Anong sinasabi? For all x, for all integers, so kahit anong integer ang ipasok natin dito, kahit anong integer ang ipasok natin dito, we have x squared minus x minus 1 will not be equal to 0. Okay? So, if up to this point it's not clear on what will be the root value of this, so let's say you get a value of 2 for your x. So you have 2 squared is 4, minus 2 is 2, minus 1 is 1. 1 is not equal to 0. Isn't it? It will not be equal to 0 because you will find here that this will only turn out to be equal to 0 if the value of x is plus 1 plus or minus the square root of 5 all over negative square root of which is not an integer. Therefore, all integers that you substitute here, you will always find x squared minus x minus 1 not equal to 0. Therefore, the truth value for this one will be true. How about number 5? Number 5, there exists an x such that x squared minus 3 is equal to 0. X squared minus 3 is equal to 0. So we can just solve this mentally. Or if you want to still see the solution of this, let's just rewrite it here. We have x squared minus 3 is equal to 0. Therefore, we have x squared equals 3. If you extract the square root, you will get x is equal to the square root of x will be the square root of 3, and the square root of 3 will not be an integer. Again, it will not be an integer. X is not an integer. But remember, our universe of this course is that x must be an integer. So, what does this tell us? There exists an x such that x squared minus 3 is equal to 0. Since our quantifier is an existential quantifier, we just need one value of x to satisfy this equation. But the possible values of x to satisfy this equation will be the square root of 3. And square root of 3 is not an integer, therefore, the possible values of x that will satisfy this equation does not belong in the universe of this course. Therefore, we cannot find any value of x that will satisfy x squared minus 3 is equal to 0, thus giving us the truth value of this proposition to be false. Okay, next. Number 6. There exists an x such that x squared is greater than 10 and x is even. This is an existential quantifier. This is an existential quantifier. X is any integer Can we find an x that will satisfy this statement such that when we get an x, it will be x squared will be greater than 10, and at the same time, x is even. So what can we do here? We just need one value. So say x is, let's say x is 6. If x is 6, what can you say about x squared? Say x is 6, isn't it that 6 squared is 36, right? Okay, so if x is 6, we, we get, if x is 6, we get 6 squared is greater than 10, right? Why? Because 6 squared is 36. So 36 is greater than 10. So we were able to find a value of x greater than 10. And at the same time, 6 is even. And since this is an existential quantifier, we just need one value of x that will satisfy this condition. And we found one. X, if x is 6, of course, we still have other possible values here. So let's say x is 4. 4 squared is 16. 16 is greater than 10. And, and 4 is even. So the, this proposition will have, this proposition will have truth value of. But if this open proposition will have the universal quantifier for all, then this will be false because not all integers will satisfy this condition. Okay, so those are some examples on determining the truth value of an open proposition wherein the open proposition has a quantifier given, either a universal quantifier or an existential quantifier, or even a combination of both. Again, just remember this. So when you are looking at the universal quantifier, all the elements in your universe of discourse must satisfy the condition given to make the proposition true. So if you can find even just one element in your universe of discourse that will violate the condition given, then the proposition will be false. On the other hand, for an existential quantifier, you just need one. You just need one. You just need one value in your universe of discourse to make the statement true. Okay? So that will be for today. So we will continue with the next section of the module in our next video lecture. Once again, good day to everybody. Stay safe and continue to enjoy our learning journey.